Okay, thank you very much. So yes, thank you for the introduction. Today I would like to talk about dynamic JavaScript and the security properties of dynamic script generation. And this is joint work with Ben Stock and Martin Johns, which are sitting here in the second row, and with our student worker Martin Wentzel, who is unfortunately not here today. So before beginning to dive into the topic, I would first like to present my agenda. So in the beginning, I will give a short technical background where I will explain a few things that are needed for the presentation, mainly like inheritance works in JavaScript and like how the same origin policy works. Afterwards, I will present an attack that was found in 2006 by Jeremiah Crossman, which is called JSON or JavaScript hijacking, also known under the term cross-site script inclusion. And what we found is that those attacks that are pretty old were based on browser quirks, but we found new ways to do that with standard JavaScript behavior. So we are generalizing the attack a bit and demonstrating that this is a severe problem in the web. And to do that, we do an empirical study where we investigated 150 top Alexa pages for this issue. And so let's start at the beginning at the technical background. So one important thing that we need to know and to understand is how prototypical inheritance works in JavaScript. So as opposed to Java or C, where class-based inheritance is used, JavaScript uses a prototypical inheritance approach. And it works like this. So instead of inheriting classes from other classes, JavaScript inherits objects directly from other objects. And if you create an object in JavaScript, here's an example where we just use an object literal with a property A to create a new object. The JavaScript engine will create this object, and this object will have a pointer to its prototype. And by default, if you don't provide a prototype, this object will point to object.prototype, which again has a prototype pointer which points to null. So this object, it's very similar to Java, where all the classes inherit from object. So now you can use this object. Let's say we have object 1, and we now would like to create a new object that inherits from object 1. So we can just do so by using the object.create function and say, okay, we want something that inherits from object 1, and we name it object 2. Now object 2 has also a prototype property, and this prototype property points to object 1, which points to object.prototype, which points to null. So when we now do an property lookup on object 2, the JavaScript engine will walk up the prototype chain. So it will first look at object 2 and see, well, is there a property named like the thing that I would look up? Here, this is the property A. So it will find object 2 doesn't have the property A, so it will look at the object's prototype, which is in that case object 1, and it will find the property A, and then it will return the 1. So basically, the property A is inherited from the other object. This is a very important thing, and we need it later on for one of the attacks. Another important concept that I need to introduce is the same origin policy. So the same origin policy is basically the most principal security policy that we have implemented in browsers. And it basically isolates different web applications from each other. And it's the reason why an attacker page is not able to read your emails in another window that is opened in the same browser. And it works like this. So I have an example on this slide. And we have two servers, attacker.org, which is attacker controlled, and email.com. And email.com is a legitimate website that has a webmail interface, and you might be authenticated to it. And what the attacker is able to do here is to lure a victim onto his website. So a victim with this browser serves to attacker.org. And in theory, attacker.org would be able to load a piece of JavaScript, and this JavaScript is capable of sending HTTP requests. So it could, in theory, send an HTTP request with the cookies of the browser attached to email.com, which authenticates the user to email.com, and then it would be able to read the response and basically access the content that is stored in the webmail interface on email.com. But that's a very undesirable property because we don't want attacker.org to read our emails. And that's what the same origin policy prevents. And the same origin policy basically prevents communication of active content in the browser, here this JavaScript, to objects that share the same origin. And the origin is defined by the protocol, the port, and the domain that was used to retrieve the object. So here we see the JavaScript is executed in the context of attacker.org, and the request goes to email.org, so the browser would prevent the response from being read by JavaScript. So the attacker has no means to read your emails on email.com. And when we talk about web security, all of the attacks target the same origin policy somehow. So usually all the attacks try to circumvent or do anything to the same origin policy to leak data or to do something that is forbidden by the same origin policy. And one such attack is JSON or JavaScript hijacking. And this is an attack that was discovered in 2006 by Jeremiah Crossman, and it was discovered in Gmail. So what Gmail did back then is that it hosted a JSON file. And this JSON file was dynamically generated based on the cookie of a user, and it contained the address book of the currently authenticated user. And you can see it's an array literal, and it contains different records, and it's basically the entries in the address book. And what Jeremiah Crossman did is the following. So he set up a website, attacker.org, and he was able to lure a victim onto that page. And so what we just learned is that the same origin policy protects us from attacker.org accessing this file. Attacker.org is not able to read the source code. But what the attacker is able to do, he is able to include this file in a script tag, because script tags are somehow exempt from the same origin policy. So script tags are able to reference third-party resources, and this will generate an HTTP request where the cookies will be attached by the browser, and the Gmail will then generate this JSON file, hand it back to the browser, and the browser will just execute it as JavaScript. The source code is not being passed to the attacker, but just executed. And what we can see here, a JSON file is also a valid JavaScript. So it would execute, it would see, oh, it's an array literal, so it will create an instance of an array, but it will never pass the reference of the array somewhere. So the attacker is, in theory, not able to access this. But what Jeremiah Crossman found out is that whenever there is an array literal, the JavaScript engine will invoke the array constructor. And the array constructor is something that is locally accessible in attacker.org. So what Jeremiah Crossman did is he just overrode the array constructor and included that Gmail JSON file, and this would, the JavaScript engine would see there's an array literal, it would invoke the array constructor and pass over the data to the array constructor. And that's where he got hands on the data and got a reference. So he was able to leak data across domain boundaries. But this attack happened in 2006, and in the meanwhile, it was fixed. So what is the current state of this attack that we refer to as cross-site script inclusion for the rest of this presentation? So the current state is that mainly the attack was based on a browser quirk, that the browser invoked the array constructor that was accessible by the user, and it was fixed by not passing that data to the globally accessible array constructor anymore. Since then, there have been a few other vectors that mainly target JSON and comma-separated value files, but all of the attacks were based on browser quirks. And whenever a browser quirk appeared, there was one in IE and there was one in Firefox, it was fixed. So, but when we looked at this, we wondered, so the attacker uses a script tag to reference a file that looks similar to JavaScript. So JSON file parses as JavaScript, and also some comma-separated value files parse as JavaScript. But when we searched for it online, we were not able to find any publicly available research that looks at actual JavaScript files. So we're using a script tag, why we have never looked at script files. And so there may be a few reasons. So one reason might be that script files are always static and there's no like private data that is of interest for an attacker to steal. Or maybe there are such files that contain this data, but the data cannot be leaked because we have no way of like getting the data out as an attacker. So we thought, oh, that's interesting to investigate. So we did the first investigation. We conducted an empirical study, and we wanted to answer the question whether there are files, JavaScript files that contain sensitive user data. Or in other words, whether there are JavaScript files that are automatically or dynamically generated at runtime based on the cookie of the user or of the authenticated session. And what we did to do that is we first created a browser extension. And the browser extension is capable of detecting these scripts. And it does so by investigating and monitoring all the scripts that we find in a browsing session and then it would request this script 2 times, once with session cookies attached to it, and once without session cookies attached to it. And then we simply diffed the files. And if there's a difference in the files between authenticated and non-authenticated context, there must be some kind of dynamic generation of this JavaScript. So this extension is basically hinting us to potential candidates of scripts that might be dynamically generated and might have some data in there. What we did then is we went to the Alexa top 500 web pages, and we picked out the first 150 pages that allowed us a registration free of charge, where we were able to register an account without social security numbers of strange countries that we were not able to have, or phone numbers, and also important that we were able to understand, either by Google Translate or by natively speaking the language. So what we did with that 150 sites, we registered accounts for them and seeded these accounts with personal data. So for example, in a shopping site, we put stuff into a shopping cart, we created wish lists. In an webmail client, we sent emails. On a calendar app, we created calendar entries and so on. So we carefully seeded these things. And then basically we used our extension while interacting with the site. So we then interacted and used all the functionalities of the sites, and our extension recorded all the scripts to see whether we can find some of these scripts. And the results were kind of surprising to us. So in total, we investigated 150 pages, and 1/3 of them used dynamic script generation. So 49 domains had some kind of script that was generated based on the cookie. And we then manually investigated those scripts, and we found that 34 websites of these 150 websites have unique identifiers in that script. So there might be an email address in the script, source code in a variable, there might be your account ID of that given web application, or it might be your name, or anything that uniquely identifies you as a user. So this could be used for de-anonymization if you can get hold of that data or leak that data somehow. Then we further investigated, and we found 15 domains that had personalized data in there. We found scripts that contained snippets of emails. We found scripts that contained calendar entries. We found birth dates, your location, your school, and so on. So all the data that we seeded in the beginning. And we even found 7 pages that had cross-site request forgery and authentication tokens inside the scripts. So to answer the questions, are there JavaScript files that contain user-sensitive data? We can clearly say yes. 1/3 of the web pages have these scripts, and there is some interesting data in script files. So the other question that we had is, well, if there's data in these JavaScript files, can we leak them somehow? Can an attacker by visiting the attacker-controlled website, can he leak the data in the script files? So I would now like to quickly revise the attacker model. That is pretty clear how it works. So we now have a set of vulnerable web pages, and I call it here vuln.com. And this vulnerable web page has some form of dynamic script. And we are the attackers, right? We can set up a host, attacker.org, and we are able to lure a victim onto that page. So now the victim is there, and what we can do, it's a JavaScript file that we found, so we can simply include that dynamic JavaScript into our page. This will make the browser send a cookie to vuln.com. The vuln.com will then have a server-side script that dynamically generates the script source that it will deliver to the browser. This will be delivered to the browser. The attacker cannot read the source code, but it will be executed by the JavaScript engine. And what the attacker is capable of doing, he can observe the side effects that this execution has. So the attacker is almighty in his own page, so he can set up arbitrary malicious JavaScript before executing that script and after executing that script to monitor what is going on. And well, we found different ways of leaking data, and I will just present 3 of them. So the first is very obvious. So we found a lot of scripts that contained just global variables. So there was a global variable in the file which was called first name. It contained your name, and it's pretty easy to leak a global variable, right? A global variable is accessible from any other script in the file. Well, so you can simply access the thing, and then you have the name of the visitor, basically. Another thing that is very straightforward is when such data is passed to global function. So we figured out that a lot of websites split their functionality. So they have like a base class or library that contains all the functionality that is commonly used, and then they have application-specific code. And the application-specific code contains mostly the private data and will then call the library that has the common functionality. And that we can see here. We have here a local variable that is not accessible to the attacker directly. It's called email and contains an email. And the email is handed over to a library call. And it's pretty easy and straightforward for an attacker to leak that data. So the data, before executing that script, he can just set up that library object and just define a function that is called like the function that the legitimate script calls. And then he can just execute the script, the dynamic script, and he again has access to the user, to the data. So this is pretty straightforward and pretty easy to understand. We also found a few more complex ways to leak data, and also to leak data that is not accessible easily or is not passed to global functions. And I will only present one of them, because those are almost enough to leak all the data that we found in the scripts. So one interesting case that we found is this one. So in this example, we see an array, and the array is called secret values, and it might contain some records or some maybe your wish list or anything that is user sensitive. And what happened is that on that secret values array, we saw a function call for each. And it seems that this is just a local function call. We have the instance, we call a local method of the instance, and then we iterate through the secrets, and the secrets are never written to the global scope. But that's not true because of the prototypical inheritance of JavaScript. So as we learned before, when you do a property lookup, the interpreter will check whether the object that has this certain property. And this is the case here for the for each function. So we call the for each function on this array, and so we will check, has this array object the for each function? And this is not the case. An array instance doesn't have a for each. The for each is defined in the prototype of the array, which is array.prototype.forEach. And array.prototype.forEach is a global function that can be overwritten by anybody. So here you can see our attacker's code. So we are simply overriding that array prototype for each. And the interesting thing here is when you call a function on an object, this reference or this keyword will point to that object. So we are calling for each on secret values, so that this reference of the for each function points to the secret array. So basically the attacker can just access the secret array by accessing this or sending it anywhere. So this enabled us to leak a local variable that should in theory not be publicly accessible by another script. And we also found some more complex scenarios how you can leak data, but I don't have the time to explain this in this presentation. So maybe check the paper or come to us after the presentation. So let's reevaluate. So we had 49 domains that made use of dynamic scripts, and in total we were able to exploit 40 of them. So almost 80% of the scripts were vulnerable to the attacks presented. And the reason for that 9 scripts to be not exploitable is that we were not able to guess the URL. So there was some kind of dynamic URL, and for the attack to work, the attacker needs to know how to include the script into his page. And one of the reasons was that there were a few applications that passed session identifiers inside the URL instead of the cookie. So we were not able to guess that session identifiers, and thus we were not able to generate the URL to include this in the page. But we were mainly able to exploit most of the things. And I think developers are not aware at all that this issue even exists. So what I would like to do now is to just give some anecdotal examples of how exploitation looked like and what were we able to do with the data that was contained in the script. And I will just tell you about 3 interesting cases. So the first interesting case is about reading email subjects and senders. So we found an email provider, and this email provider had a widget on his website, and when you go to the main site, it would preview the first 5 emails in your inbox. Actually, these first 5 emails were contained inside a script which generated that widget. So by just including that script, you were able to leak the first 5 messages, including the sender and the subject, and the date, and a message ID. So basically, you were able to read a visitor's inbox, or at least the first 5 emails. The second case that was very interesting. So we found a news website. It was just an arbitrary news website. You can register to it and log into it. And it has a script that contained the cross-site request forgery token. So by visiting attacker.org was able to include that script, leak the CSRF token, and then we were able to do this CSRF attack. And then, well, it was a news site, so there's not much functionality. Maybe you can set a post to a news article. But there was an interesting fact that there was a profile page, and the profile page contained an XSS. And the XSS was in theory not exploitable because only the user himself was able to set that field, and only the user himself was able to see that field. So, but what we were able to do with the CSRF, we were able to send a profile change request and put that XSS payload into the profile page. So we exploited a vulnerability that was not exploitable before. And interestingly, this page had a Facebook integration. So all the users that logged in via Facebook automatically gave rights to that application. And the rights were pretty the permissions were pretty broad. And one fun thing that we did, we just created a Facebook post in the name of the user. So we used the OAuth token that was stored inside the application through the XSS attack and just posted things on Facebook. So just by visiting the page. And you can use this to create a worm or something where you, like, say, click on this link, and when other people click on this link, you do the same, and so on and so forth. Okay, and then we had a third case, which was the most severe thing that we found. So we found a script in a file hoster. And the file hoster had a very Ajax-driven UI, so there were a lot of XHRs going on and a lot of requesting, and these XHRs needed to be authenticated. And for this to happen, they had an authentication token, and to deliver this to the front end, they just put the authentication token into a script. So we were able to access this authentication token, and basically were able to hijack the full account of the victim. Because the authentication token was valid for a very, very long time, I think we had access a few weeks, or it might even work today. We never tried, but it was at least a few weeks that this was valid, and we were able to do anything. We were able to upload files to the account, we were able to delete files, we were able to access all the files, and a very interesting thing is that we were even able to compromise other services with that, because the file hoster had a single sign-on solution with other services that it offered. And when you pass an authentication token to the single sign-on solution of another service, it would automatically authenticate you to that other service. So we also got access to Calendar and Photo app and some other applications that were running on the same domain or hosted by the same server. Okay, so that's pretty severe attacks, but it's just some showcases. So we found a lot of other interesting things to do. So we are almost at the end, but we should also talk about preventing XSSI vulnerabilities. So how do we deal with that attacks? So nobody seemed to be aware, so we need to have some protections. And the first thing is that I want to mention is that our attacks are not based on browser quirks. It's just pure JavaScript functionality. You cannot, like the attack of Jeremiah Crossman, you cannot easily fix it on a browser level. The other thing that you might try to attempt is to create a JavaScript that does not leak the data. And we think this is very difficult and you should never do it. You should, basically there are two different solutions to that problem. You could either prevent the script from being included by a third party, and there are different solutions to do that. For example, you could stick to SIG referrer checking, and whenever you see something that is not your own page, you don't deliver the script to the user, but this is very error prone and does not work in all the cases. Or you could put some random token into the URL. For example, something that is similar to a cross-site request forgery token, so that the attacker cannot guess the URL. So then he cannot include it and cannot steal the data. So, but we think that the right solution to approach this problem is to actually not put sensitive data into JavaScript files and not dynamically generate JavaScript. You should have static JavaScript code and separate sensitive data from it by putting the sensitive data into a data provisioning service that is properly protected by the same origin policy, and just have static JavaScript code in your not so much protected JavaScript file. Okay, that's it. I'm almost at the end, but I would like to mention one quick thing, and I don't have a lot of time. XSSI and the content security policy. So the content security policy is a new mechanism to prevent XSS, and basically it requires you to move all inline script out to external files. And inline scripts are not prone to our attack because you cannot include inline script across domain boundaries. Now, if you employ content security policy and you just blindly move out all the inline script to external files because it's required, you might end up in situations where you create XSSI vulnerabilities. So whenever you introduce CSP, don't blindly move scripts out, but protect the inline scripts if they contain sensitive data. Okay, with that I would like to conclude. So what did we do? We investigated the security of dynamic JavaScript generation. We demonstrated that there are a lot of dynamic JavaScripts that contain sensitive user data. We also found ways to leak that sensitive user data. And we conducted a study on 150 popular websites. We're able to see that 1/3 of these pages use dynamic JavaScript, and that 80% of the sites that use dynamic JavaScript are vulnerable to the attacks that we presented today. And the consequences of an attack range from simple privacy violation, like something like de-anonymization, to full account compromise. But our study was very small, and the main reason for this was that we had to manually seed all the accounts, manually click on everything. That made it very difficult to scale up this research. And the introduction of CSP might likely make the problem worse. With this, I would like to thank you for your attention, and I'm ready for questions.
Shorchen, Microsoft Research. Yeah, this is very interesting work. My question is, suppose people are not allowed to generate dynamic JavaScript. Does that mean that they always need 2 round trips to do the work?
Yes, that's the main disadvantage. So whenever performance is critical and whenever this round trip would incur a performance hit, you would rather stick to URLs that contain tokens. But developers forget to put tokens into things or forget to validate token correctly. So there's a brittle solution that I would not really recommend. And I think the problem will go away with HTTP2, where you can have multiple requests and so on. It's much quicker and much more performant than the actual ways. Yeah.
Okay, great. Thank you.
Thank you for the talk, Sebastian. Can you explain a little bit the separation of static JavaScript and this dynamic data store that you mentioned?
Okay, sure. I had too little time in the end. So basically, what we see is that JavaScript gets dynamically generated, and people start putting like variables with emails and so on into it. And we think that you shouldn't do that. You shouldn't generate a JavaScript dynamically and put the data in, but you should keep your files static and have a second data provisioning service. So you have a static JavaScript file and you load the data at runtime, and you load it from an API that is protected against such a thing. So you put up a data provisioning service that returns something that is not parsable JavaScript, that cannot be included by a script.
Okay, so you cannot poison the prototype of the static script in order to access the data from the data store.
Yeah, because when you include the script, it's executed in the origin of attacker.org, right? So you cannot access, if the data provisioning service is protected by the same origin policy, you cannot get the data. You can poison the prototype, but you will never get, the browser will prevent the JavaScript from getting data.
Thanks.
Just one comment, this is Christoph Kern, Google. Just one comment about the performance aspect of splitting this. The flip side of this is that then your JavaScript is typically large, is going to be completely static, which means it's cacheable, right? So you probably actually might be better off in the big scheme of things for
Yes,
users.
yes, good point. Other questions? Otherwise, thank you.